Hello everyone, welcome to Exploding Chemistry by Teacher Susan. Today, we are going to look into thermochemistry. What is thermochemistry? Thermochemistry concerns itself with the relation between chemical reactions and thermal energy. Thermal energy is the energy of motions of particles such as atoms, molecules, or ions, while chemical reactions can either release or receive heat from or to surrounding. There are two types of chemical reaction under thermochemistry. It is exothermic reaction and endothermic reaction. Now let us look at the first chemical reaction, which is exothermic reaction. Exothermic reactions are chemical reactions that release heat to surrounding. Common observation that normally can be obtained. Number 1. Final thermometer reading is higher than initial thermometer reading. And number 2. The container like beaker or conical flask will normally turn warm or hot. And the common inference that can be used to deduce exothermic reactions are temperature rise and heat is released. Let us look at the two daily examples involving exothermic reaction. Number 1 is the hot pack. Number 2, burning any love letters or papers with fire. Next, we are going to look into the energy level diagram for exothermic reaction. As you can see, the energy content of the reactants is always higher than the energy content of products. And when we look into delta H, which is the heat of reaction, we will always see a symbol negative indicates heat release to the environment. Coming up next is endothermic reactions. Endothermic reactions are chemical reactions that absorb heat from surrounding. The common observations are: number 1. Final thermometer reading is lower than initial thermometer reading. Number 2. The containers like beakers or conical flasks will turn chill or cold. And the common inference that can be used to deduce endothermic reactions are temperature drop or heat is absorbed. Well, let's look at some daily example involving endothermic reaction. Number 1, baking cakes. Number 2, cold pack that can be used to reduce pain in athlete. Coming up next is the energy level diagram for endothermic reaction. As you can see here, the energy content of the reactants is lower than the energy content of the products. And the delta H, which is the heat of reaction for endothermic reaction, must carry a positive charge, indicates heat is absorbed from surrounding. The example that I'm using here is dissolving ammonium chloride powder in water. How do we calculate the value for heat of reaction? There are many ways. But first of all, I would like to introduce to you the calculation for the heat of reaction based on the average bond enthalpies, or what we call them as the bond energy. As you can see on your screen, this is an example of the average bond enthalpy chart involving a few different examples of covalent bond. Before we move on to the calculation, let's have a look. Step 1, we shall calculate the total heat absorbed to break the chemical bonds in the reactants. Step 2, we shall calculate the total heat release when forming back all the chemical bonds in product. Step 3, calculating the heat change by minusing the heat absorbed during the bond breaking with the heat release during the bond forming. What does it mean? Okay, let's look at example 1 for further explanation. Okay, we are looking at the reaction between hydrogen gas
and chlorine gas in order to produce hydrogen chloride gas. Okay, before we can move on to the calculation for this heat enthalpy involving the covalent compound, first thing that I want you all to do is to convert the following chemical equation by drawing the structural formula for each of them. So for hydrogen gas, we will have H single bond H, chlorine gas Cl single bond Cl, and for hydrogen chloride gas, H single bond chlorine times 2. Okay, referring to the bond energy chart that I provide in my previous video, we can know that the bond energy involving hydrogen and hydrogen, it is 436 kilojoule, chlorine single bond chlorine 242 kilojoule, and each of the hydrogen chlorine single covalent bond will be 431 kilojoule. Now, next step, what are we going to do? We are going to calculate the total energy absorbed in breaking the chemical bond. We need energy to be absorbed in breaking all the chemical bond in the reactants, which I draw in this red color section. In order to break the bond, we want to breaking the chemical bond, whatever chemical bond that we have, and normally in this case we refer to the covalent bond. So the total energy that we need, the total energy that absorbed to break the hydrogen single covalent bond and chlorine single covalent bond will be the total amount between 436 kilojoule and 242 kilojoule, which means a total of 678 kilojoule. And to form back a chemical bond, when we are going to form back chemical bond, we need to release a total amount of energy. In order to release the total amount of energy, we need to check what kind of chemical bond that involved here. When we are forming two reactants of hydrogen chloride, they involve formation of hydrogen chlorine single covalent bond for 2 times. Each hydrogen chloride single covalent bond, when they form each of them, they will release 431 kilojoule of energy. In order for us to get 2 stable hydrogen chloride gas, we need to release 431 times 2 kilojoule of energy, which means they are going to release 862 kilojoule of energy. While the last step involving here is to calculate the heat change. What is a heat change? Heat of reaction that involved in the formation of hydrogen chloride gas. We take the total energy that we need to break the chemical bond minus the total amount of energy that released during the formation of chemical bond, which in the end we have negative 184 kilojoule per mole. This is the amount of energy needed in order for the whole chemical reaction to be carried out. And what is this negative symbol stand for? This negative symbol stand for at the end of the chemical reaction, a total amount of 184 kilojoule of heat energy is being released to the environment. And this symbol negative also telling us that the chemical reaction between hydrogen gas and chlorine gas in the formation of 2 mole of hydrogen chloride is an exothermic reaction. I repeat, this chemical reaction is an exothermic reaction because the delta H for the end reaction carry a negative magnitude. And this negative symbol stands for a total amount of 184 kilojoule of energy is being released out to the environment. So when heat is being released out to the environment, the chemical reaction is an exothermic reaction. If I want to record the observation for this chemical reaction, I can see that the final temperature which recorded by the thermometer reading, my observation will be final thermometer reading is higher than initial thermometer reading. Okay guys, okay? Thank you for your...
I hope you guys can understand the explanation based on example 1. As an enhancement, please try to do example number 2 involving the formation of ammonia gas in Haber process, HOTS question 1 which is a substitution of ethane with chlorine gas, and HOTS question number 2 which is complete combustion of ethanol in excess oxygen. To check the answer and the explanation, click on to the YouTube channel. Before I end my session, thank you very much for your time and your effort. Please remember to subscribe and hit the notification bell because more video is waiting for you. Thank you.